Okay, today we're going to talk about random walks. There are more great applications to random walks in computer science than possibly have time for, so we'll see a couple, but I hope you'll like it. Okay, so let me tell you about my basic day. So every morning I get to school at 9 o'clock. I'm like, all right, time to work. Let's do it. So I get down to my math with the sigmas and whatnot. Okay. Now, then time ticks by, 1 minute later, and I'm like, math is kind of hard. So maybe I'll continue working on my math with probability 40%. But with probability 60%, I'll be like, I need a break. So I'll surf the web. Okay. This is very addictive. So another minute may tick by, and the probability I will return to work is minimal. And the probability I will continue wasting time is high. But I'll start to feel angsty, you know. So maybe another minute will pass, and I'm like, maybe I should check my email, which is kind of like working, because I have infinite work-related email. So of course, the probability if I'm not going to jump to work or go back to surfing, that I'll go to email is the remaining probability, 30%. And then another minute will tick by, and perhaps I'll get an action item in my email and be like, all right, I guess I got to get back to work. So that will happen with some probability. And then since I have infinite amounts of email, there's another chance, 50%, I'll just keep doing that. So that's it. So that's my basic day. Now you know how I spend my time. So just to recap, 9 a.m., I'm in some state. Let's say I start out working. And then perhaps after 1 minute, maybe I continue to work. That's a 40% chance. And then maybe I'll start to waste time. That's a 60% chance. And then, I don't know, probably I'll still be doing that in the next minute. And there's maybe a 30% chance that I'll start doing email, etc. Okay, you guys get the picture? You understand this example? Yeah. Okay, so this is an example of a Markov chain, which is a very general kind of random walk. And Markov chains are of extreme importance in many areas of computer science, especially learning theory, machine learning. People love Markov chains there. So what is a Markov chain in general? I gave you an example. Maybe you could kind of guess the definition, but the basic object is a directed graph. Okay, not an undirected one, but a directed graph. And it's quite important that self-loops are okay. You can have a vertex with an arrow to itself. And in this class, we're going to always assume that the directed graph is strongly connected. You know what that means, right? For any two vertices, you can go from one to the other, and from there, back. Okay, so it's not going to be disconnected at all. That's not an assumption everybody always makes, but we will always make this assumption. And each edge, like in the previous example, is labeled by a positive probability. Okay, which is the probability of transitioning along that edge. And at each node, which sometimes is called a state in Markov chains, the probabilities on the outgoing edges sum up to what? I think somebody said 1. Yeah, 1. Because it sort of expresses all the different possibilities you can go to. Yes?
So is it need to be positive or non-negative?
Usually it doesn't really matter. Usually you put in an arrow if it's positive. So yeah, so usually when you draw it, you only draw an arrow if the probability of it is strictly positive. So if there's some missing edges, going from work to email, that just means 0 probability. Was that your question? Okay. Great. All right, so that's basically the definition of what a Markov chain is, but now let's talk about how it acts. So here's a more state example than the one I gave you. It has 4 nodes, which I labeled 1, 2, 3, 4, and you can see there's various arrows going various places, including self-loops. And at each node, unless I screwed it up, the sum of the outgoing probabilities is indeed 1. So for example, if you're in state 3, with probability 90%, you go to state 4, and with probability 10%, you go to state 2. Okay, so let me give you some notation. We're pretty much always going to write n for the number of states. And basically, once you know the number of states, the entire Markov chain is described by sort of all the probabilities, right? And in fact, what you really just need to know is for each state I and other state j, what's the probability of going from I to j. which, as I just said, is 0 if there's no arrow in the picture, but otherwise it's what's written on the arrow. And what you can do is take all these potentially n squared probabilities, for each I and for each j, which also includes I, and you can collect them into a matrix, which is what we do. Okay, and that's called the transition matrix for the Markov chain. It totally defines the Markov chain, and the ijth entry is the probability of going from state I to state j, in one step. Does it make sense? Okay, if you're a mathematician, you would normally write matrices like this with the I and j as subscripts, but that's very annoying eventually for us. So I'm going to write it more computer science-y way, k brackets I comma j. So it just means the ij entry of the matrix k. Okay, so this Markov chain picture actually corresponds to this matrix, and they're equivalent. So for example, this is row number 3. It's the one I talked about. And this is column 1, 2, 3, 4. This says that if you're in state 3, you go to state 1 with probability 0, state 2 with probability 1, state 3 with probability 0, and state 4 with probability 0.9. What property will all the rows of this matrix have? Yeah, they'll sum up to 1, because a row corresponds to where you start. What? Oh, yeah. Okay, I did screw it up. The upper right-hand corner should be 0.1. Thank you. Oh, what? Oh, man. 0.2, 0.7, 0.1. No, this should be 0.1. Yeah. Okay. Let's see if I can fix it. Oh, man. Oh, fuck. Oh, I don't need your sympathy. Okay, I guess Pitt is losing. Okay. Okay, the rows sum up to 1. This is called the stochastic matrix. Okay, one more piece of notation. So in Markov chains, right, time ticks by. We denote time by t. It goes 0, 1, 2, 3, up, etc. And we write xt for the state at time t, okay, which is usually a number between 1 and n. Now, the initial state is kind of up to you. Somebody will tell you, okay, you start in this state, whatever. But then once the initial state x0 is defined, then x1, x2, and x3 are generated by this random process. Okay, so they're random variables. x0 somebody gives you, then x1 through x whatever are random variables. Okay, so if this was this chain for my day, then suppose I tell you, okay, I'm going to start out by working. Then x1, if I go to surf in the next step, would be s. I'm using letters instead of numbers here, but you get the point. X2 would be e in this case. X3 is something. Okay, and it goes on forever. Okay, so here's our Markov chain. Here's the picture. Here's the matrix that also defines it, the transition matrix. So I'll now ask you some easy questions, and we'll ramp up to harder questions. Okay, so what is this? Suppose I tell you I start in the state of working, W. What's the probability that I'm in the surfing state at time 1? You can just say it aloud. Yes, 0.6. It's in the matrix right here. Okay, what's this one? Probability I'm in surfing given that I started email at time 0? Yep, it's 0. Okay, what is, suppose I tell you that you condition on that you're in state S at time 5. What's the probability that you're working at time 6? Yeah, it's still the same. Okay, so I mean, this transition matrix also tells you, the transitions for each step. And it doesn't really matter. One aspect of Markov chains, which is sometimes made a big deal of, although it's not that amazing, is that to figure out where you're going to go next, you only need to know where you are now. It doesn't matter how you got there. So we don't need to worry about what x0 through x4 were to figure out what x6 may be. It just matters where you are at time 5. Okay, so in general, what is this? Yeah, it's Kij. Okay, so this translation matrix is for every time step. Yes? Yes. Yeah, the question was about like a situation where the probabilities change over time. That thing exists. I think it's called a time inhomogeneous Markov chain, but it's studied like far more rarely than this case. Okay, now I'll get a little bit harder. So please compute this. Suppose I tell you that I start out in the surfing state. What's the probability I'm working at time 2? I'll give you a second. No, it's not 0.1. No. Wait, what did you say? Yes, this person is good at arithmetic. It's 0.25, while also good at applying the law of total probability. So let's figure out how we got that answer. Basically, you just have to condition or consider all possible places that I could have been at time 1. Okay? So there's going to be 3 cases, either work, surf, or email. And by the law of total probability, we can figure it out by this conditioning rule. So first, I want to consider the probability I'm working at time 1, given that I started here. And I need to multiply that by then the probability that I'm working at time 2, which is what I care about, condition on both of these facts. Okay, now as we've seen before, the probability that I'm working at time 2, it doesn't really matter like what was happening at time 0. Just what matters what was happening at time 1. So actually, I could just erase this bit. Okay, and now these 2 quantities, we both know, we know how to get both of them out of the matrix, right? We saw that last time, so this is, given that I'm surfing, I'm working in the next step, it's probability 0.1. Given that I'm working in the first step, the probability I'm working in the next step is 0.4, so there's that. And we need to do the same computation for each of the other 2 intermediate states I might be in, either surfing or emailing. Okay, so I can read all these 9 numbers out of the table. And it's this computation. And yeah, it turns out to be 0.25. Very good. Okay, so the numbers don't really matter, but is the idea of how we figure that out by conditioning on what x1 is clear? Okay, so now let's ask a general question. Let's say you have a general Markov chain, and you have 2 states I and j, and I tell you you're in state I at time 0. What's the probability you're in state j at time 2? Yeah? Pardon me? Okay, so you're very sophisticated. You've got the final answer. So let's get the final answer in a more slow fashion. Okay, it's the same idea, though. You just have to condition in all the places you might have been at time 1. Okay, so it's it's a sum over all possible states, k, going from 1 to n, of like the probability you get to state k at time 1, given that you started in state I, times the probability that you get to state j, your final destination, at time 2, given that you were in state k at time 1. Okay, that's the law of total probability. And now these are things that are entries in the transition matrix. This is k, I, k, and this is k, kj. Sorry for the k overlap. Okay, so it's this expression, which looks pretty nice. And that's, before on the previous slide, we indeed had the sum of 3 things of the form probability times probability. But then if you look at this more carefully, you see it's exactly like the formula for the entry in a matrix if you do like a matrix product of k times k. Right? If you look, this is matrix k, this is matrix k. This is like the ith row dotted with the jth column, which is like the I, comma, j entry of k times k, k squared. Okay? So this probability, the probability of going from I to j in exactly 2 steps is exactly all the entries of the k, matrix k squared. Okay, so that's convenient. You can figure out the 2-step transition probability just by squaring the basic matrix k. Any question about that? Okay, so probably you can guess this one. If I start in state I, what's the probability I'm in state j at time 3? Yeah, it's the k cubed entry of, or it's the ij entry of k cubed. So, we could do that. We could compute that, let's say, by conditioning on x2. It's the same pattern. And for this, the probability that you're in state little k at time 2, given that you were in state I at time 0, we just decided is the ik entry of k squared. This is the kj entry of k. So again, this is the ij entry of a matrix product, k squared times k. Okay, and in general, for t steps, the probability that you go from state I to state j in exactly t steps is the ij entry of the matrix k raised to the power t. Okay, now there's one aspect of this that was a little ad hoc. It's like we always had to like have somebody tell you like what state you start in. You may as well like allow a more general situation where like even your starting state is chosen randomly somehow. Okay? So this is something that's often done, that assume that the starting state, x0, is also chosen from some random distribution. For example, maybe I just tell you that like in the morning at 9 o'clock, I start out working 50% of the time, I start out surfing 20% and emailing 30%. Okay, then x0 and all of x1, x2, x3, etc. are random variables. I like to call this a distribution vector. I mean, it tells you a probability distribution over each of the states. It just means a non-negative vector whose entries add up to 1. Okay, and we usually write the distribution vector for the initial state as pi 0. Pi is the first letter in probability, so it's like a probability for each of the states for the initial time step. Okay. Okay, let's take this example. Suppose I tell you this is my the probability distribution over my initial state. This is our old friend, the Markov chain. Okay, so can somebody tell me the probability that I'm in this case, that I'm working at time 1? Okay. Oh, yeah, you're always skipping. I want the number here. Yeah. So, okay. I mean, it's a similar computation, right? So, I mean, we'll get to what you said. But, 50% of the time I start out working. And then I continue to work with probability 40%. 20% of the time I start out surfing. And the probability that I go back to work is 10%. And similar calculation for the third possibility. Okay, so it's some number. Okay, so that's similar to before. And let's do the general case now. So suppose you have some n-state Markov chain. I give you some initial probability distribution for the initial state, pi 0. Let's try to figure out your state, the probability you're in each state, let's say state j at time 1. Well, again, you condition on where you are to start at time 0. And it's the sum over all possible starting states I of the probability you start in that state times the probability you go to the target state j, given that you started at state I. Okay, so this quantity is what in terms of what we have on the slide? It's an entry in a certain matrix. That matrix is a vector. Yes. So pi 0 is a vector indexed by the states, and its ith entry is the probability that you start in state I. And what is this in terms of like matrices we like? The probability of being state j at time 1 given you start in state I? Yeah, this is kij. Okay? So if you stare at this for a second, you also see that this is like an entry that you would get if you did this row vector times this matrix. You see that the jth entry, if you were to do this row vector times this matrix, would be this row vector dot the jth column of k, which is exactly what's going on here. Okay, so this is the jth entry of pi 0 dot k. Okay, so what that tells you is for each state j, if you want to know what's the probability you're there at time 1, it's like the jth entry of pi 0 times k. So kind of if pi 0 is the vector that tells you the probabilities for all the starting states, then the vector pi 0 times k tells you the probabilities you're in each of the states at time 1. Does it make sense? Okay, so we usually write pi 1 for the vector of probabilities for where you are at time 1. And this is what we just computed. Okay, and we also know that, if you raise k to the tth power, it sort of tells you the transition probabilities for doing exactly t steps. So if we write pi t for your probabilities of being at each state in time t, then pi t is, the initial distribution pi 0 times the matrix k to the t. Okay. So now I'll talk about an important distribution, an important concept for Markov chains, which is called the invariant distribution, or sometimes the stationary distribution. Okay, so let's go back to my day once more. And remember that the ijth entry of k to the power of t tells me the probability of go from state I to state j in exactly t time. So let's just figure out what these matrices are, okay, which you can do by typing them into MATLAB or some other such program. Well, this one you could do by hand, but then it gets too boring to continue. So that's k squared. It tells you something like if I'm emailing, then in 2 steps, the probability I'm surfing is 30%. Okay, this is k cubed, whatever. Okay, this is k to the 10th. Now you may see something kind of interesting about these entries. So let's see what happens in half an hour. Now it looks more interesting. Obviously, you notice something about these entries of this matrix, right? Okay, so what's going on here? Can somebody tell me the intuitive meaning of what's going on with this seeming coincidence in the matrix? Yeah? Yeah, that's exactly right. So let's remember what this means. Each entry here, let's say in the first row, this tells me the probability I'll be doing either working, surfing, or emailing at time 30, given that I started working. And it's these numbers. And the second row tells me the probability I'll be in each of the states, given that I started out surfing, and given that I started out emailing. And you see it's practically the same in each case. So what it's saying is, when t is large, when you've been doing this like Markov chain for a while, basically, the distribution, the probability that you're in each of the states, doesn't really matter where you started. Like, once t gets big enough, it's kind of a wash. And, in the long run, you kind of forget about where you started. And you sort of tend to one limiting distribution of being in each of the states. Okay, so this limiting row, assuming, it exists, and like we're not fooling ourselves by some amazing coincidence, but this almost always happens for any Markov chain. This limiting row, assuming it exists, is called the invariant distribution for k, and it's denoted by just plain pi. Okay, it's also a row vector that tells you a probability for each state. Okay, so this really, this experiment, well, it's evidence, tells me that like in the long run, if I, doing my day for a long time, for a large value of time, 29% of the time I'm working, 44% of the time I'm surfing, 26.5% of the time I'm on email, which sounds about right. Okay. Okay, so this is a very interesting thing to learn about the Markov chain. Once I give it to you, it's not obvious what these limiting probabilities are, but it seems like something you might want to know if you want to see how I spend my time. So, it seems you could do this by just raising k to large powers, but that's very tiresome to do by hand. So let's see if we can figure out another way to do it. Okay, so here's the idea. I call this an invariant distribution for a real reason. It kind of says, imagine, I've been doing this Markov chain for a long time, and now I'm in each of the states with some probability. Then if I do it for like one more step, I'm probably still going to be in the states with the same probability, right? Because, if t is a really long time, then t plus 1 is also a really long time. So, what's going on is that this limiting distribution pi, of me being in each of the states, has the property that, like, if I were to start in that distribution, which is kind of like starting my day, like, many minutes into the future, and then do one more step, I would still be in that distribution. Okay, this is a property that sort of the long time distribution will have, that like sort of once you get into this state where you're in each of the states with some probability, you kind of stay in that state as time goes by. And this is exactly saying that if you do start in state pi and do one step, you stay in state pi. I mean probability distribution pi. Does that make sense? Okay, so the good thing is this will help us calculate pi because actually, if you know k, it's like some explicit matrix with numbers, and you're trying to figure out pi, then this is, if you think about it, and we'll see on the next slide, this is actually a system of linear equations if you think about the pi values as unknowns. So you can solve it. Okay, so let's write down this equation, pi equals pi k. Say this is k. And say this is pi. It has like 3 unknowns that we're solving for, and we have this fact. So if I do this matrix vector multiplication on the right, then I'll get this vector dotted with this, and that should equal pi w, and similar for this vector dotted and this vector dotted. So if I just expand out the right-hand side, I actually get 3 equations in 3 unknowns. That looks great. Although actually, if you try to solve this, you'll see that it's like underdetermined. Like, even though it looks like you have 3 equations, like one of them you can actually derive from the other 2. So that looks bad because it means it looks like it's not really defining pi. But actually, there's one more equation about pi that we can add. Can somebody tell me some other equation about pi that we could put in? Yes? Yeah, that's right. It's supposed to be a distribution, right? So the entries it's a probability vector, so they should sum up to 1. So we can put in this equation too. And now we can solve these equations. There's 3 variables and 3 unknowns. You can probably solve it by hand. Otherwise, again, you can use a computer. And you get the exact solution. Okay, it's like 10 over 34 for working, 15 over 34 for surfing, and 9 over 34 for emailing, which are exactly these limiting percentages that we saw when we were raising the matrix to large powers. Okay, so this is something you should remember how to do. Like if I give you a Markov chain, figure out what the invariant probability distribution is. Okay, so that I sort of did by example, and it's not totally clear that it was going to work out. Like there are some things I just sort of told you that one of these equations would be redundant, and another thing you might worry about is like if you solve a system of linear equations, like sometimes you get negative numbers, right, for the values, but then it wouldn't make sense. Like you can't have a negative probability. Maybe until next lecture. But it turns out that everything always works out great. And like this is the fundamental theorem of Markov chains that tells us that there's always an invariant distribution. So it says whenever you have a Markov chain with finitely many states, and it's strongly connected, like I said we'd always assume, then there's always a unique invariant distribution pi. And you can get it by solving this equation, pi equals pi k. Okay, so that tells you that you can take this theorem for granted. It's actually somewhat of a pain to prove. Not that bad, though. But we'll just use it. And furthermore, pi is also, I told you can get pi by solving these equations, but we came to it intuitively by thinking about raising k to some large powers. And pi will actually also always be the limiting rows of the large powers of k, unless some very stupid issue happens called periodicity, which I don't want to dwell on, but I'll illustrate for you. This is like an extremely stupid Markov chain, but technically it counts according to the definitions. There's 2 states, and you just like switch back and forth with them as the time goes. So you can see that in the long run, you can't just say like, oh, I'll definitely be in this state with some probability and some state with some probability, because it depends on like the parity of time. So this is the transition matrix, and if you start raising it to powers, you'll see that, well, k squared is this, which makes sense. If you do exactly 2 steps, then if you start in state 1, you go to state 1 with probability 1, and state 2 is probability 0, and vice versa. In k cubed, it's the other way, and k fourth, it's the other way. So you see, if you keep raising k to a power, it's not like the rows go to some fixed limits. Okay, but it's only happening because of this like annoying fact that like there's like some even odd issue going on. This will rarely come up. But in fact, even without worrying about this, it's still true. This theorem is still true, that there's a unique distribution satisfying this. And in this case, it's the distribution half the probability in state 1 and half the probability in state 2. Yeah, 1 second. And what it says is, if you start your day by like flipping a coin and going to state 1 with probability a half and state 2 with probability a half, and then you come back any time in the future, like at any time t, it's still the case that you're in probability state 1 with probability a half and state 2 with probability a half. Yeah? That's a good question. It seems like it has something to do with the fact that this doesn't look too random, like, there's transitions you take with probability exactly 1. But can even happen in some cases where that's not true. If you imagine, like, I'll give some example maybe later. And then another property this has, even in this case, these still sort of represent long-time averages in some sense. Like, if you run this, stupid chain for like 1,000,000 steps, it's still true that sort of in the long run, on average, half the time you're in state 1 and half the time you're in state 2. So this still has some meaning even in these periodic chains that are annoying. Okay, I want to do one more kind of theory-ish topic, and then we'll get to some more application type things. And this is a very pleasant fact. So I want to think now about how long it takes you if you start in a state U to come back to state U for the first time. So let's say you have some Markov chain, and you figured out its invariant distribution pi. And suppose you really care about a certain state called U. So you look at the invariant distribution, and you see it's 15/34. So somehow in the long run, you're spending this fraction of your time at state U. So if you walked in this Markov chain for like a really large number of steps n, what would be the expected number of times, okay, roughly speaking, that you would expect to be in state U? What? Yeah, n times this fraction, 15/34. This slide is a bit unrigorous, by the way, but we'll give you the proper thing later. Okay, so you're probably going to be in state U about this many times. So you can think of like a giant timeline, and like it has n steps, and about this many of the times you're at state U. So what would you, think is the average time length between successive visits to state U? Yeah? Yeah. You have about, this many dots on a line of length n, so, the average gap between them would be about n over that, which is like 34/15, or the reciprocal of this. That kind of makes sense, right? I mean, if this fraction of the time, 15/34, you're in some state, it seems like, the expected amount of time you'll take between successive visits to that state is 1 over that. Does it seem reasonable? Okay, so, it seems kind of reasonable, and luckily it's actually true. So, I mean, it's not very hard to turn this into a theorem. And here's the theorem, called mean first recurrence theorem. This will be our last theorem for a little while. If you have a Markov chain and you know its invariant distribution pi, and I call m sub u the expected number of steps it would take you if you started at u until you first come back to u again, then that equals 1 over pi of u. Okay, and actually notice in this theorem it has nothing to do with like walking for a long time, or like it doesn't assume that you've been like walking for a long time before you get to u. You can start at u at like time 0, wait until the first time you get back to u, and the expected amount of time that takes, this theorem tells us, is 1 over pi u. Okay, so we'll remember this for the future. And this is a little summary of all the things we've talked about for Markov chains. You have a transition matrix K, whose ij entry tells you the probability of going from I to j in one step. The tth power tells you about the probabilities for going from I to j in exactly t steps. If you know the distribution on states initially pi 0, then you can get the distribution on states at time t by doing pi 0 times k. Every chain has a unique invariant distribution that has the property, if you start in that distribution and then walk, you just always stay in exactly that distribution. And the time to go from u back to itself is, on average, 1 over pi of u. OK. Any questions right now? OK, let's do a brief application. This is about PageRank, which you may have heard of. This is how Google, well, at some point, this is how Google ranked its web pages in search results. OK, so I don't know if you were like born back in 1997, but I was there. And let me tell you that it was very painful to find things on the web. Actually, there were like 300,000 websites total back then, which is not that many. But still, it was very frustrating. So like the best search engine back there was called Alta Vista, which doesn't exist anymore. This is what it looked like. So why was it so bad? They didn't have very sophisticated algorithms. So let's say you search for like CMU, right? Then it would find all the pages that contain the text CMU, and then it would basically just like spit them back to you. And I guess maybe it would sort it by like which page like had the word CMU on it the most times. Which you can see, around 1997, like spammers were starting to get sophisticated, right? You could see this is not a very good idea. OK, so it's very hard to find anything. So this is right around the time when there was a very good idea that came along about how to rank web pages. And it was had by 2 different groups. These guys, maybe you recognize them. Who are these guys? Yeah, it's Larry Page and Sergey Brin, the founders of Google. They were graduate students in computer science at Stanford. And does anybody know who this guy is? No? OK, this is a guy called John Kleinberg. He was and is a computer science professor at Cornell. And they had they had basically the exact same bright idea, and they talked to each other about it, in fact, in summer of '97. And OK, so they took this idea. These guys became 20 billionaires. But actually, you don't have to feel too bad for this guy, Kleinberg, because he won the Nevin Linna Prize, which is kind of like the Fields Medal or the Nobel Prize for theoretical computer science. So he got his too. OK, so what was this idea? I mean, I could spend like a whole lecture talking about this. I will spend 1 slide talking about it, but maybe it'll pique your interest. You can read about it. Basically, you need to figure out like a way to like decide which are the good web pages, right? And you want to put the good web pages and the important ones on the top. So one aspect of the idea was we can use, instead of trying to like use some AI or something to analyze the text and figure out if it's good, just take all the pages that have whatever CMU on them and look at the hyperlink structure. OK, there's hyperlinks between them. And maybe this will indicate something about the importance. OK? Like maybe if a page has a lot of links pointing to it, it's important. Although you could sort of defeat that if you're a spammer by like taking the page you want people to see and making many other pages that point to it. So the idea somehow, but it's a bit recursive. That should only be true if those 1 million other pages are also considered important because they have links coming into them. And also, if you have a page that has like many, many links going out from it, then like, it's not like this page should get like 1 vote for each of these pages. Maybe it should get like 1/3 of its importance transferred to those pages. So you can think about this idea for a while, and one interesting thing that you might think of is this idea of the random surfer model. So imagine all these pages, and imagine a web surfer who uses it like a Markov chain. Maybe they're looking at some page, and at each step, at a first pass, you might say they go to a random hyperlink on the page, and that they keep following random hyperlinks around and around the pages. But you should actually, it's better to put a little twist where, OK, with maybe some probability like 85%, they do that. And with the remaining probability, like maybe 15%, you imagine they just jump to a totally random page. Like instead of clicking a link, they just type something random into their address bar. OK, and now this is like a Markov chain, right, where the states are the pages. And you maybe might imagine that, the higher the probability a random surfer is looking at a page, the more important it is. And this is the idea of PageRank. So it's to literally like take this, compute the invariant distribution, which is sort of like the long-term probabilities with which a random surfer is visiting each of these pages, and rank the pages this way. Like the higher pi of u is, the more important it is. And yeah, this was their idea in '97, and they implemented it, and it was like immediately like infinitely better than every other search engine, and thereby they became the one and only super powerful search engine. So actually, it's not. This is how they used to do it. They wrote papers about it. Now it's like all a trade secret. Google is like a black hole for research, so nobody exactly knows what's going on there. But okay, this is what they used to do, and it seemed to work well back then. One other thing I found out is you would think, why is it called PageRank? You're like, because it's about ranking pages, right? No, yeah, it's because Larry Page named it after himself. Yeah. Okay, so that's an interesting application and money-making application of Markov chains in computer science. Actually, let me ask one more question. Why do you think it's a good idea to have this alpha parameter? What's wrong with just having, the server just goes to random hyperlinks? Yeah, you can get trapped in a loop, for example. For example, if you don't have this, then the graph is probably not strongly connected, right? You can have just like a bunch of pages that all point to each other. And in particular, also, like, a spammer can like make a bunch of pages that all point to each other and have like no outgoing links. So like if you somehow start there, you'll never go out, and it'll look like these are super important pages. Okay, so this is why it's important to have this jumping out probability. Okay, so let's come back to theory for a while. We're actually going to spend most of the rest of the class on like a special case of Markov chain. So it's good. We went from the like general setting to like an easier setting. And it's going to be about when you do a random walk on an undirected graph. Okay, because at least in computer science theory, it's more common to have undirected graphs. So the notion here is probably just what you might guess. Like, I'm going to assume that you have an undirected graph, also connected always, like this. And the nodes are the states, and in each state, you just go to a random neighbor. Okay, so if you're at this state, it has 3 neighbors. You just pick them each with probability 1/3 and go to them. Okay, and that's your walk. You hop around the nodes. Let me add some notation here. I'm always going to write n for the number of nodes and m for the number of edges. Oh, I forgot to add this part on the last slide. I'm also going to write d sub I for the degree of the ith node. Okay, so, with this picture, it doesn't look like a Markov chain, but it really is equivalent to a Markov chain if you draw it like more complicatedly, right? So this is the equivalent actual Markov chain, and here's this node. You go to here, here, and here, all with probability 1/3. Or like if you're here, you go there with probability 1/2 each. Okay, so people see that the random walk on the undirected graph is still a Markov chain. Okay. All right, well, let's think about all the basics again. What is the transition matrix K? Well, if you've got this picture, then you can just read it off this picture, but usually you don't take the effort to draw this picture. You just want to stare at this diagram. Okay, so here's the undirected graph here, and I put 1, 2, 3, 4 as labels for the vertices. So how can we get the transition matrix? Well, before we get there, there's a well-known matrix that's associated to any undirected graph, which is the adjacency matrix, okay, where, again, the rows and columns are indexed by the nodes, and you just put a 1 if there's an edge there. Okay, so this is the adjacency matrix for this graph. Okay, now somebody tell me, how do I get the transition matrix sort of easily from the adjacency matrix? Yeah? Exactly. Divide each row by the sum of the row. The transition matrix has the property, in particular, that the rows sum up to 1, right? And here, there's 3 outgoing edges for vertex 1, so you should divide by 3. It should be 1/3, 1/3, 1/3. Okay, so in particular, you should divide each row by the degree of the associated vertex. Okay, so 3, 2, 3, 2 in this case. So this is the transition matrix. Notice, by the way, this is a small point, but this matrix, the adjacency matrix, is always symmetric. The transition matrix is not necessarily symmetric. It's symmetric if all the degrees are the same. Okay, so the next thing in the basic Markov chain theory we talked about is like, all right, now what is the invariant distribution? Let's think about that intuitively for a second. All right, so assuming this, we don't worry about this periodicity thing, it's also the same as the limiting distribution, like the limiting probabilities for each of the vertices if you walk for a really long time. Actually, as a side note, when you're doing random walks on undirected graphs, this periodicity condition is even rarer. It only comes up if the graph is bipartite. Okay? If the graph is bipartite, then you do have this weird even-odd thing where, like, on the odd steps you're on one side and on the even steps you're on the other side. But otherwise, you don't have to worry about this periodicity. Okay, so let's go back to thinking about the invariant distribution, pi. So, okay, let's take this graph for an example. Imagine you're just like doing a random walk on this graph. You're like hopping around from vertex to vertex. Somebody tell me, what vertex do you think you're most likely to be in, over time? The center one. Yeah, why? Yeah, it has the highest degree. I mean, this is all intuition, but yeah, this one has the most incoming edges, so it seems like you'd be there most often. You might wonder, maybe this would be like a dream awesome fact if like the invariant distribution for a vertex u is just proportional to its degree. That would be kind of intuitive. Well, sometimes your dreams can come true. That is a theorem. It's not hard to prove. We'll prove it. And it says in a random walk on an undirected graph, here's the invariant distribution. It's basically the degrees, but you have to normalize, right? So the probabilities add up to 1. So I guess you all know if you sum up the degrees of a graph, it's like you're counting each edge twice. So you get 2 times m. Okay, so the invariant distribution is the long-term probability of being in state I is di over 2m. Okay, does it make sense? I'll give some examples soon, but let me just prove this. The proof is short-ish. Okay, so I'm telling you, like, pi is the invariant distribution. Now you're checking me. Okay, so it's supposed to have the property that pi equals pi k. That if you start in this distribution and do one step, you stay in this distribution. Okay, so let's just do pi k. That's pi. This is k. Aij I wrote as the entry of the adjacency matrix. So we divide all the first row by d1 and the second row by d1. So now let's look at what happens if you do this matrix vector product. Let me just do the first entry. It's this row dot this column. You see the d's all cancel out, right? You have like d1 and over d1 here. So that's good. So when you do this row dot this row, you have a 1 over 2m hanging out from here. And then what remains is the sum of the a's in this column. So like a11 plus a21 plus a31 up to plus an1. And that exactly represents the number of vertices that have an edge to vertex 1. Right? Which is the degree of vertex 1. So, which is d1. So this row dot this column is exactly d1 over 2m. And same for all the other columns. And that's pi. So you just check that pi times k, this pi I told you, is indeed pi. So if you didn't catch that, you can try it at home. But this tells you that everything you wanted is true. Let me do one more corollary of this. Remember this theorem that says if you do a random walk and you're interested, if I start at a state v and I want to know what's the average number of steps until I come back to v, it's just the reciprocal of the invariant distribution at v. I just told you that pi of v is dv over 2m. So this expected time to go from v to v is 2m over dv. Okay, I'll give some examples that will illustrate this. Okay, so you remember the formulas? Okay, so here's a very simple graph. It has 3 vertices. Okay, so somebody tell me what the invariant distribution is for this graph. How many edges are there? 2. So 2 times m is 4. And the degrees are 1, 2, and 1. So the invariant distribution is this. Okay, this is also the long-term probability of being in each state. Let's take a look at the middle state. Actually, it's kind of obvious that it's right there, because if you're at this state, pretty much, you're actually at this state every other step. This is a bipartite graph. So if you're here, you go left or right, but then you always come back. So in the limit, half the time you are in the middle state. And by symmetry, the other ones are quarter each. Okay, so this, remember, is the expected time to go from a state to back to itself. It's just the reciprocal, so it's 4, 2, and 4. Again, it's easy to see for the middle guy. It's not even just the average time to go from here back to itself. You always go from here back to itself in 2 steps. Here it's less clear because you can start here, you either go and come back, that's 2 steps. You do that half the time. Or you go here, here, come back, that's 4 steps, a quarter of the time. I guess 6 steps, an eighth of the time, etc. On average, it's 4. Okay, let's generalize. This is the path graph, and it's slightly more convenient here to have n plus 1 nodes, okay? So this is the path graph with n plus 1 nodes. How many edges are there? N, yeah? Okay, so that's m is n, so 2m is 2n. And the degrees are 1, 2, 2, 2, 2, 2, 2, 2, 1. Okay, so the invariant distribution looks like this. I don't know if this is intuitive or not. For example, you see in the limit, for each of the internal nodes, you're there like equally often, probably 1 over n. You might think that like maybe you would stay around the middle more, but it's not true. It is less likely, though, that you'll be at an endpoint, because whenever you go to the endpoint, you go away on the next step. Okay, so we can take all the reciprocals, and we get that these are the recurrence times. Okay, so in particular, let's say if you start at the leftmost point, and you walk for a while, and you wait till you get back to the leftmost point, on average, it takes 2n steps. Okay, I'm going to do 2 more examples. This is the clique, or the complete graph on n nodes. How many edges are there? N choose 2, right? M is n choose 2, which is this. And the degree of each node is n minus 1. So the invariant distribution is given by the degree over 2 times m, right? Which is, degree over 2 times m is 1 over n. Okay, which tells us the invariant distribution is 1 over n for each node, which makes sense, right? I mean, if you're doing a random walk on this graph, then it's completely symmetric. Indeed, like in the limit, or on average, or at each node with probability 1 over n. And the expected time to, if I start at some node until I get back to that node is also n. Because I always do 1 step, and then for all the subsequent steps, there's a 1 over n minus 1 chance I'll come back. So it's like 1 plus a geometric with parameter 1 over n minus 1. Okay. This graph is called lollipop. I did not make that name up. That's the real name of this graph. You take a clique on n over 2 vertices, and then you put on this like tail or handle or whatever, which is a path of n over 2 vertices. I'm not going to do the calculations. They're easy, but you can do them at home. I'll just tell you that for a vertex over in the clique, the recurrence time is n over 2. If I start here, how much time do I spend before I come back here? On average, something like n over 2 steps. But out here, it's more like n squared. It's like n squared over 8. If you start here, you might come back to here, but there's some chance that you kind of get trapped in this like clique part of the lollipop, and it takes you a long time to come back. We'll see a bit more about that shortly. Okay, I want to prove one more theorem about random walks in undirected graphs, and then we'll end with examples and things. This is a bit technical, but it's not hard. So here's the theorem. Well, here's the proposition. Say you have a graph G, and just fix any edge, which I'm going to call U0 and V0. And now I'm going to look at this. I call it M sub UV. Similar. I'm going to start at V0. Actually, this should say M sub V0, VU. I start at V0, and I'm going to go around until the first time I hit U0. And I'm going to look at the expected number of steps that takes. The theorem is that it's at most 2m. It's actually at most 2m minus 1. Okay, so these guys are connected by an edge. So there's like, if you start at V0, there's a 1 over this degree chance that you'll go to U0 in like 1 step, which is pretty good. But there's some other chance that you'll just like start walking around, and it'll like take you a while to get to U0. Okay, but this theorem tells you it's not too long you have to wait. Is the statement clear? Okay, the proof is like a little bit weird, but it's not hard. Here's the proof. Let's look at V0. It's connected to U0, and it might be connected to some other vertices too. Okay, so let's just call the other vertices that it's connected to U1, U2, up to UK, however many there are. Okay, so there they are in the picture. Okay, so let's use the theorem that we know about the expected time if you start at V0 to come back to V0. Okay, we know this theorem. The expected number of steps to start at V0, walk around and come back to V0 for the first time. It's 1 over the invariant probability for V0, which is this, 2m over the degree. All right, now let's think about this experiment. I start at V0. I'm going to walk around until I come to V0. A natural thing to do is to condition on the first step. See where you go in the first step. Okay, so we're going to use the law of total probability there. So I'm going to, in the first step, you could go to any one of these u's. There's k of them, so, well, k plus 1 of them. So I'm going to just sum over all of them. I goes from 0 to k of the probability that you go to ui in the first step times the expectation of the number of steps it takes you overall to go from v to v, given that your first step went to ui. Okay, because it could make a difference depending on where you go in your first step. Okay, is that okay so far? Okay, well, this is easy. For each of the neighbors, you go there with probability 1 over the degree. And here, how many steps does it take you? It takes you 1, the first step, and then you're at ui, and so then you need to compute by linearity of expectation the expected number of steps it takes you to go from ui to v0. Okay, I'm almost done. The rest fits on this slide. So this is a sum of a bunch of things. Something for u0, something for u1, something for uk. We don't actually care about these u's. I mean, we're still interested in this, about going from u0 to v0. So these are non-negative things. Let's just drop everything in the sum except for the I equals 0 term. So this is at least what you get just from the I0 term, which is 1 over the degree, and then times 1 plus the expected number of steps it takes you to go from u0 to v0. Okay, so why are we done? Yeah? Yeah, now we're done. It's just algebra. I mean, you can multiply both sides by dv0. You get 2m is at least 1 plus this thing. That's what you care about. Subtract 1 from both sides. Get the expected number of steps to go from u0 to v0 is at most 2m minus 1. Okay, so that's kind of, as I said, it's kind of a weird proof. Like, I don't know. It's short, at least. Okay, and it proves this fact about, if you're going from u to v, and u and v are actually connected by an edge, then it doesn't take you that long. Any questions? Okay, so this was actually really only a lemma for the real theorem I care about. This is the real theorem I care about. It's the same question, but just u and v are any old vertices. Okay, because that's more thing you would be curious about. I have some connected graph G. U and v are any old vertices, and I'm curious, if I start at u, how long does it take me on average until I get to v? And the theorem is it's at most 2mn, which is also not that much. I mean, 2mn. Can somebody kind of maybe suggest a proof or a proof idea? Yeah, how about you?
If there's n nodes in a graph, they can't be more than n steps apart.
Yeah.
Because they have to all be connected. So the number of expected times you have to go from to connecting things is less than 2n, and you have to do that less than n times.
Yeah, that's about it. Is that what you're going to say, Anshu? Yeah. So here's how you can say it. Concerned about u versus v. As was stated, there's at most n nodes in the graph, and it's connected. So there's some path from u to v, a path of edges. Okay, let's say it goes through these w's. There's at most n of them. And now we're curious about the amount of time it takes you to go from u to v. And I'm going to upper bound that by making you do a harder task. I'm not just going to say, okay, I'm curious about you starting at u and ending at v. I'm curious about like how long does it take you on average if like you must go through all the w's as checkpoints. Like you start at u, you have to go to v1, the w1 as a checkpoint. Then you have to go through w2. Then you have to go through w3, all the way up to v. How long does this like more painful thing take on average? It's an upper bound. Well, it's still not so bad. Again, by linearity of expectation, it's the expected number of steps it takes you from going from u to w1, expected number of steps from w1 to w2, and so forth. And all of these are edges, so we can apply the result on the previous slide to bound all of them by at most 2m. Okay, so the overall bound is 2mn. Okay, this is going to be like our last theorem. Let me just add one more thing. M, in the worst case, there's like n choose 2 edges, so it's like n squared over 2. So you can also, if you're a bit lazy, just upper bound this whole thing by n cubed. Okay, so to go from any vertex to any other vertex on average takes at most n cubed steps. Let's do some examples. Okay, this is the path node graph again, and I'm curious about going from the one endpoint to the other. So this is u, this is v. Okay, so we would apply the theorem, and it says it's at most 2mn. In this case, m is also like n, so this is like 2n squared, basically. It's O of n squared. Now, this is an upper bound. The expected amount of time, this says that the expected amount of time to go from u to v on average is at most n squared. So do you think that is close to tight, or do you think you maybe get there faster? You might guess that maybe it would be like O of n. It only has to travel O of n, although granted it can go, go back and forth. Maybe I'll take a survey. Who thinks it's like O of n squared, and who thinks it's O of n? Who thinks it's O of n squared? Some. O of n? Less? It is O of n squared, actually. So you'll see maybe either in the homework or recitation, it really does take like something like a constant times n squared steps. Like you do really waste like a lot of time like going back and forth on average before you get across a path. Okay, how about the clique on n nodes? Doesn't really matter where u and v are, so just take any old u and v. Okay, the theorem says if you start at u, the expected amount of time to hit v is at most 2mn. M is like n squared here, n squared over 2. So that's at most n cubed. So this tells us that it takes at most n cubed steps. Who thinks that is a good bound? It's true, but it doesn't seem like it should take n cubed steps. Actually, what is the expected amount of time it takes you to go from u to v? Can somebody tell me? Although this bound is true, it's not very sharp. Yeah? Pardon me? Nope, lower. Oh, that's a good point, though. You're saying u and v are connected by an edge, so we can apply like the lemma to show that it's at most 2m minus 1. That's true, so that would be like n squared. It's actually even lower. What's that? Yeah. Just think about the experiment. Forget the theorems for a second. You're at u. You take a step. It takes you somewhere. Maybe it takes you to v. But every time you take a step, you have a 1 over n minus 1 chance of going directly to v. So it's like you keep flipping a coin with probability of success 1 over n minus 1. So on average, it takes you n minus 1 tries to get there. Is there a question there? All right. OK, so the theorem is true, but it's not always sharp. Let me do this last example. Go back to the lollipop. OK, so let's pick the most interesting case. U is something in the clique part, and v is the end of the path. So we're interested in, if you start here, how long does it take you to get to v on average? Well, the theorem tells us at most n cubed. And actually, this time it is sharp. It really does take you like proportional to n cubed steps to get from here to here. It's a very slow process, because like you start here, you like walk around here most of the time. It's only about like every nth step that you even have a chance to start getting out. Then even once you get out, you still have to cross this path, which we know takes, on average, like n squared. But it's even worse, because if you go back and forth, every time you get back here, you have a chance of like wasting a bunch of time in here again. So you can think about more why this is true, but it really does take n cubed steps on average to go from here to here. Okay. We have just enough time for an application to computer science or life. So let's suppose that you are in a labyrinth and you have very little memory. I don't know if you could see Guy Pearce there. It's bad lighting. Okay, so maybe you just have enough memory. You can't remember anything. You can like scratch some notes on an Etch-a-Sketch or tattoo them on your abs or whatever. But you still want to get out of this labyrinth. Well, let's just start with forget the memory thing. Let's think about just getting out of a maze. So this is a very simple computer science problem called connectivity, or con for short. The input to the problem is a graph. And like here I will tell you it might be disconnected, OK? I'm not assuming it's connected. It might be disconnected. And you also get as input u and v. And the task is yes or no. Are u and v connected by path? Okay, in other words, are u and v in the same connected component or not? This is a pretty easy problem. Can somebody tell me how to solve this problem? I mean, in like a few words. There's like well-known algorithms that do it, yeah? Yeah, breadth first search is a common way. Start at u and do breadth first search and see if you get to v or not. Or you can do depth first search or whatever. It's very easy to solve this in like time O of m, where m is the number of edges. Now, if you do this, one thing you're going to have to do is you have to like mark the nodes. You know, you start at u and like everything is unmarked, and you start doing breadth first search, and you like mark. I've been here, I've been here, I've been here. Okay, so you need to use like n bits of memory at least to keep track of these marks. Okay, I assume that the input is like read only. Okay, you with me so far? Okay, so let's go back to Memento. Now I make it a challenge for you, okay? You must do this task, but you cannot use any memory. You cannot allocate any memory. You cannot have an array. Nothing. You can have like some local variables, like a constant number of them, like 10. Okay, now how can you do it? Now it almost seems impossible, right? I mean, you cannot keep track of where you've been. It's like crazy, right? You can try an algorithm. You cannot do any like breadth first search. You cannot do depth first search because like you cannot record like any information basically. So what can you do? Well, based on what the lecture has been about, you have a question or a suggestion? Okay.
You would walk randomly, say, on a ridiculous order, say, n to the 6 many steps, and if you haven't made it to v at the end of that, it's probably.
Yes, excellent, very good. So the suggestion, which was also made, I don't know, 36 years ago or something, by Alunis, Karp, Lipton, Lovaas, and Rakov, was a randomized algorithm. And this was back in the day, so like it was like amazing to think of the idea of using randomness in an algorithm. Maybe now we're not so shocked. We've seen this and like randomized algorithms for primality testing and stuff, but this was surprising. And it's an extremely simple algorithm, just as was suggested. Here's the algorithm. This is it. You start at u. Let's say you start z set to u. And I'm going to run time for 1,000 times n cubed steps. And I'll just do a random walk. So I'll do z as a random neighbor of z. I'll just go along. And if I see v, then I'm like, great, they're connected. And I return yes. And if I like time out, then I'm just going to return no. And there's a chance I screw up because maybe I never got to v, even though they are connected. But this is my algorithm. Okay, it takes about O of n cubed time. But let's talk about the memory thing. Why? I mean, let's just double check that really this uses no extra memory besides a few variables. It's fairly clear. Let's assume a variable can hold like a number between 1 and n, like an index to the vertices. Okay, so this is one variable, z. This is maybe not completely clear how to do it, right? Because this variable t seems like it needs to go up to n cubed. And I'm assuming a variable can hold between 1 and n. Somebody suggest how to do this, though? You can do it with like 3 or 4 variables. You can just go like for t1 goes from 1 to n, for t2 goes from 1 to n, for t3 goes from 1 to n. T0 can go from 1 to 1,000. Or you can just take this triple loop and write it 1,000 times. Great. So that takes like 4 variables to count up to n cubed. Doing this, you have to like look at the graph. So maybe you have to like compute the degree of z. That takes like a couple of variables. Okay, so you can do this whole thing with like 7 variables or something, and no additional memory. Okay, so that's kind of awesome. And now let's think about how good this algorithm is. I mean, this is a good start, right? Suppose the true answer is no. U and V are actually not connected in the input. Then your algorithm is awesome. Your algorithm will always say no, right? It's never going to get from U to V, so it's definitely always going to time out and return no. So in one case, it's golden. Now, the other case is not so clear, but here's a claim I'm going to make, that if the true answer is yes, that U and V are really connected, I claim this algorithm says yes with probability like 99.9%. And you can make that even higher if you want by making this 1,000 bigger. So that's great. I'm going to explain this in a second, but let me just say that that's great. I mean, this algorithm, solves the problem. Okay, so why is this? It just basically follows from the things we've seen. So let's suppose the answer truly is yes, and U and V are indeed in the same connected component. It's some maybe subgraph, but it has at most n vertices still. You start at U and walk for a while. So let's not exactly worry about the algorithm, but just let's say we do a random walk starting from U, and we just keep going with no timeout until we get to V. And let t be the random variable that counts the number of steps that took. And our theorem said the expected value of t is at most n cubed. Now, that says on average, if we walk for n cubed steps, given that they're connected, it'll take us this amount of time on average, but that's not quite what's going on, right? The thing we actually more care about is, if we go for a lot more than n cubed steps, like 1,000 n cubed, like what's the probability that, even though the average is n cubed, like it'll take us more than 1,000 n cubed to get to V. And so we'll like time out wrongly. Does anybody remember what fact we can use to analyze that? I think it was sort of in one of the recitations. Yes, somebody said it. Who mumbled it? Yeah, Markov's inequality. If you remember that, it's a fact that does not really deserve a powerful name because it's very simple. So I claim, given that you know this expectation is n cubed, the probability that this random variable is bigger than 1,000 times this expectation is less than 1 over 1,000, which is 0.1%. So why is that? I mean, okay, you can remember Markov's inequality, but it's also intuitive, right? I mean, suppose for a contradiction that the chance that t is bigger than 1,000 n cubed is at least 1 over 1,000. Then already, 1 over 1,000 of the time, t is bigger than 1,000 n cubed. You multiply those together, it would tell you already that the average value of t is bigger than n cubed. But the average value of t is at most n cubed. Okay, so if you don't quite remember that, at least it's probably believable that if the average of the random variable is n cubed, it's very unlikely to be larger than 1,000 n cubed. Okay, and that is exactly what we want to know. This is exactly saying the probability that this algorithm, even though U and V are connected, will not make it from U to V in 1,000 n cubed steps is at most 0.1%. So the probability it says the right thing is 99.9%. Okay, so that's a very simple algorithm for connectivity if you have no access to memory. So actually, for 25 years, this was one of the most famous examples of a problem where we knew a randomized algorithm that solved the problem, but we did not know any deterministic algorithm that solved the problem. Much like primality testing, for a long time we knew these Miller-Rabin primality tests that were probabilistic, but we didn't know how to do it efficiently deterministically. And it seems even harder to do it deterministically. So now I take your random coins away, and you're in this maze. You got to get from U to V, or see if you can get from U to V. You cannot remember anything, basically. So now what are you going to do? You have a suggestion? Sorry? So this, what you can do, maybe what you're suggesting is you can, it's not exactly clear. Like you can start at U, go to like its first neighbor, and then if you're doing DFS, then you're at some other vertex. You go to its first neighbor, and then maybe you go to that guy's first neighbor, but you cannot remember like where you've been or even. Yeah, so you cannot remember much. If you go for like a while, it's hard to even get to the point where you try a second neighbor. You have a suggestion? Well, okay, there's two things with that. For hashing, usually if I do hashing, I use randomness to do a hash. You can try to get around that by some sort of crazy weirdo hash function. But actually, I'm not a little bit sure. So you can maybe, you're saying you follow a path, and like you want to keep track of like a hash of the path. But now let's say I want to do one more step. Maybe to figure out the hash of the new path, I have to know like what path I've followed. But I only have the hash value, so I have to like invert the hash function, wouldn't I? That seems very hard, right? I mean, normally if you think of a hash function as like a random map that takes a lot of information in, like. Okay, but basically you're saying like I have a bunch of information, like a path I want to store, and I'm going to use a hash function to like make it smaller. But like that's going to, I mean, by information theory somehow, like you cannot get something out of nothing. But, I mean, it's a reasonable idea. Any other suggestions? Yeah?
You have like a number that you interpret in base n, where each time the, because that'd be the most possible number of nodes, so each time you take the ith edge along that node that you're pointing at, and that represents the entire path. So you can search all the paths.
Yeah, this is a reasonable idea too, if I get what you're saying. Like, imagine somehow you could get like a really long number consisting of digits between 1 and n. Then you could sort of follow that as a path. Like, for each number, if I'm at a node, I'll take the next digit. It's a number between 1 and n. I'll go to that neighbor if it exists, or if it's not, I'll just go to the next one. That could potentially work if somehow, for example, the number is a long random number. But otherwise, it's a bit tricky, like, because you don't have access to randomness, and like, you also can't really store this number, so you have to generate it somehow. Actually, all these are good ideas, but it's very tough to make it work. But you can make it work, so it's very hard. So I cannot possibly explain it to you. I mean, it's very hard to explain it even in like a graduate course, but it can be done. So this guy, Omer Reingold, actually works at Microsoft now. Gave a solution, a deterministic algorithm that uses only a constant number of variables that solves the connectivity problem. That was a very famous result in theory over the last decade. Okay, that's it. So see you on Tuesday.